This is a problem on electric fields and charge distributions. We have an arc here with positive charge distributed along the arc. The observation location is at the center of the arc and it's 120 degrees. We have a small charge dq here, and we have dE, which is the electric field due to the dq, which is k times dq over r squared. dE has a y component and an x component. The y components are going to cancel out those, so all we care about is the x component, which is going to be dE times cosine theta. And r here is just the radius. So dEx is going to be dE, which we've written up here, times the cosine theta. The linear charge density is going to be Q over the area, which, since 120 degrees is a third of a full circle, we have a third 2 pi r, so we can rewrite that as 3 times Q over 2 pi r. So for dQ, we can write that as lambda, the linear charge density, times ds, and ds is going to be this radius times d theta. And this angle theta is at half of this arc between that and the radius, and it's the same on the other side as well between dE and dEx. So lambda times r d theta is dq, so we can substitute that in for dq and get this expression for dEx, and the r's cancel, so you just get one r on the bottom, as you can see here. So we integrate from 0 to 60 degrees and multiply that times 2, since we have split this into two components of 60 degrees. So we do that, we pull out the constants and anything that remains the same, like the radius, and integrate, and we get sine of theta, and just subtract sine of 60 minus sine of 0, and we get this. The 2's cancel, and we can simplify by putting back in the expression for lambda that we got in the beginning, which is 3q over 2 pi r. So then we end up with r squared in the bottom once again. And so 1.73 divided by 2 is going to be this expression, and we know that it's going to be in the x direction, so we put x hat. And that's how you find the electric field for an arc of distributed charge.